Good morning. Today we are going to see about introduction of advanced RC design. So in that advanced RC design, the methods of design of RC structures, there are three methods. So first one, limit state method, working stress method, and ultimate method. The first one, in introduction to limit state method, the structure is designed for its safety and checked for its serviceability. So in working stress method, we are designing the within the elastic limit. Here we are focusing on beyond elastic limit. And then understanding of limit state method. There are two main criteria we are focusing. First one is limit state of collapse and limit state of serviceability. And then limit state of collapse, we are focusing the severe loads, deals with structure ability to withstand more service loads and failure loads, assessed by considering potential failure modes by rupture, buckling, or overturning. And third one is resistance to bending, shear, torsion. That's why we are studying limit state of collapse, bending, tension, torsion, shear, etc. And then serviceability means the cracking, fire resistance, deflections. So these are all comes under serviceability. And then to ensure the safety serviceability. So safety means limit state method ensure the safety of the structures without any collapse. And then without excessive serviceability mean without excessive cracking and deflections. A structure are designed throughout their lifespan. For example, if you are designed for 50 years, the structure should stable for 50 years. There is safety and serviceability. And fundamentals of beam design. Designing of beam, fundamental structural engineering tasks crucial for safe and efficient load management. The process begins by assuming the section size, the size of the beam, grade of steel, grade of concrete, suited to the structure's demands. So these are the fundamentals and types of reinforced concrete beams. There are two types. First one is singly reinforced beam. Singly reinforced beam means mu less than mu limit, where mu is the ultimate moment. The factor moment is less than limiting moment. The bottom of the reinforcement resists the tensile forces. And the top reinforcement is hold the main reinforcement. This type of structure is known as singly reinforced beam. And doubly reinforced beam, the moment, factor moment exceeds the moment of resistance. It is the factor moment exceeds the limiting moment mu greater than mu limit. So these types of beams are doubly reinforced beams. And neutral axis, the role of neutral axis. It is the axis lies in the cross section of flexural member having zero stress and zero strain. This is the definition for neutral axis. Also, there are three types of section. A balance section, meaning of that the actual neutral axis is coincide with critical neutral axis, that is balance section. Second one, under-reinforced section, the actual neutral axis is less than critical neutral axis. And then one more section is that is this one, over-reinforced section, the actual neutral axis is greater than critical neutral axis. There are three types of section. So our design must be balance section or under-reinforced section. Then comparison between under-reinforced section and over-reinforced sections. In under-reinforced section, steel reaches the permissible limit first. In over-reinforced sections, concrete falls without any warning. It is brittle failure. The concrete reaches the permissible limit first. And design procedure as per the IS 456-2000. The first step is load calculations. What are the load acting on the structure? It includes dead load, live load. In case of roof slab, additionally you can include the floor finishing load. So that is our first step. So next one, effective span. What is effective span? Effective span means it is a center to center distance between the support. The supports may be RC, reinforced concrete or masonry. So effective span means, as per the code, it is a center to center distance between the supports, or clear span plus effective depth. So take whichever is, compare these two, you will take whichever is smaller. And then the dimensions. First, we are taking the dimension based on the span by depth ratio, the ratio to 12 to 15. So after that, we are confirming the depth as per the, in case of steel, Fe415, you know that D is equal to square of mu divided by 0.138 FCKBD square. Based on that, we are confirming the, that is depth required at the step 4. And then reinforcement area, in case of under reinforced section, as per IS 456-2000, one formula is that mu is equal to 0.87 FYASTD into 1 minus FYASTD divided by FCKBD. Based on that formula, we will find the required area. And then number of bars. Then how to find number of bars? We found area of steel at step 4. Number of bars equal to capital AST by small AST. Small AST is the assumed diameter. It may be for main reinforcement, you will provide 12, 16, 20, 25 and 32. And then the last step, once the design is over, we are checking the shear. There are two types of stresses. One is nominal stresses, tau V is equal to V by Vd, and the permissible stresses tau C. Permissible means allowable limit available in the IS code. Nominal shear stress, we know that stress equal to load by area, shear stress divided by area. So based on that, we are providing if tau V greater than tau C or tau V equal to tau V exceeds tau C, you have to provide shear reinforcements. So tau V less than tau C means member safe in shear, both the shear. So that the case, so no need for any shear reinforcements. And then spacing of stirrups. I know that spacing of stirrups, as per IS 456, there are two conditions, 0.15D and 300. So next one, design of columns. Column is a compression member provided to carry a compressive load. So in that column, the tied column with ties, beam, stirrups, spacing, column, lateral ties, pitch, the spacing between the ties. One more tie is that there is spiral column tied with spiral reinforcements. So and then combination of sometime this combination of steel member incorporated with the concrete, that is composites column. And then the main thing is the tributary area method. Determine the column loads. The tributary area method means, for example, consider this column. So how to find the load transferred to the column? Load acting on the column, half distance of adjacent columns, load on column is equal to area into floor load. So based on that, we are finding the tributary area. In case of interior column, the tributary area is equal to half the span to the adjacent columns, both horizontal directions, reflecting the load shearing between neighboring supports. So similar to that, you will find edge columns and corner columns, exterior columns, interior columns. And then calculation of reinforcement. You know, the minimum reinforcement is 0.8% and maximum steel is 6%. For dense congested reinforcement, the reinforcement percentage is limited to 4%. Based on that, you will find reinforcements. And then classification of columns, axially loaded within the axis, and then uniaxial means the column have one axial load and one moment because of the eccentricity. And then biaxial means the column have one load and two moments, that is biaxial. And then axial means it is lies in the axis, and then eccentric means it is away from the axis. And then design of column. First you will check the slenderness limits. Based on the slenderness ratio, we are finding the column is short or long. It is the ratio between effective height to the least lateral dimensions. And then after the confirmation of, that eccentricity, Ex and Ey, the value is greater than Emax is less than 26. So based on that, we can find the axial load column can be used. So after that, the formula Pu is equal to 0.4 FCKAG plus 0.67 Fy, 0.4 FCK into EAC. Based on that, so we are designing the column. Also the number of bars the same as the design of beams. And the lateral ties as per the IS 456 guidelines, least lateral dimension 16 times the diameter of bar. There are two types. The spacing is 16 times the diameter of bar and 300 mm. And the diameter is 1/4 of diameter of longitudinal bar or 6 mm. So based on that, you will choose the diameter and spacing of the ties. It may be a circular ties, depends on the shape of the column. And then deflections. There are two types of deflections. One is short-term deflections and long-term deflections. Another name of short-term deflection is immediate deflections. So occurs instantly when load is applied to their structural members. Another one, long-term deflection, because of creep, shrinkage and cracking. So based on that, there are 4 methods finding the deflections: double integration method, moment area method, conjugate beam method. Already you studied in strength of material and mechanics of solids. And the next one is principle of virtual work. Then importance distinguishing short and long-term deflections. The main issue is serviceability issues and design implications. And as per the code, we are finding the deflections. I know the formula: simply supported beam with UDL deflections. Formula already studied in strength of material and mechanics of solids. 5 divided by 384 W L power 4 by EI. And simply supported beam with concentrated load, PL cube by 48 EI, the deflections formula. Case of cantilever beam with UDL, WL power 4 by 8 EI. Same cantilever beam with load at free end, with the free end load, PL cube by 3 EI. And then due to gravity loads, the deflection is equal to AX power divided by EI, using Morse theorem. So that's all about advanced design of RC structures. Today we looked into limit set design and design of limit set design, further fundamentals of limit set design, serviceability, then design of beams, design of sections, followed by design of columns, at the end deflections calculations. So thank you.